space. So in the last class we saw that for an isotropic material, now we have S is equal to gamma naught of I of C times I plus gamma 1 of I of C times C plus gamma 2 of invariance of C times C squared. So this is something that we saw in the last class. And today we will look at certain approximations to this. So suppose now you want to find out a linear approximation to this. So that means your C is small in some norm sense. Then what is the result that you will get? Okay, so we'll have the following theorem. Theorem, assuming that the constants gamma I are prime indifferent, are differentiable. So these pi of x and lambda of x and mu of x, these are constants, right? And so of course the material is allowed to be inhomogeneous, and so that is why these constants can be different at different points. But basically what we are doing is that we are just carrying out a linearization of this particular part, right? So you can see that now, so let us just assume that it's a natural state, right? So natural state means that in the reference configuration the stress is going to be 0. So in that particular case this pi of x can be said to be 0, right? So if for a natural state, this pi of x is just the pi of x can be taken to be 0. So it's just going to be lambda times space of E times I plus 2 mu times E plus order E. So we are going to basically neglect this order E under some approximation, right? So suppose if the strains are small, so this E is small in some norm sense, correct? That means, let us say E times E, right? So much less than 1, let us say. And then we can make this approximation that basically we retain only up to the linear terms, and then we can drop the non-linear terms here. So I'm not going to go through the process of linearization of this because that is fairly straightforward, and that is also given in the book. So the process of getting from this particular equation to this equation is given in the book. So that, I mean, it's just a very straightforward linearization, so I'm not going through that process. but I'm just stating here the final result that we get after the linearization here. Okay, so so what happens if we now drop all the order E terms? Okay, then we get a material model that is known as the Savannah Kickoff material model. Okay, so we are going to discuss that particular model now. Terms in the previous expression. So what you get is that S of E is equal to lambda of trace of E times identity plus 2 mu for all E belonging to sim. So this is the relation that you get by dropping all the non-linear terms. Okay, so now basically this is a linear stress strain relation. But the strain displacement relation is still non-linear. So that is very, very important. But U to E is half of del U plus del U transpose plus del U transpose del U is still non-linear. So basically this material model, okay, is materially linear, but geometrically non-linear. Geometrically non-linear. Okay, so do not confuse this with linear elasticity. In linear elasticity, the stress strain relation is linear, but the strain displacement relation is also linear, right? So here, the strain displacement relation is non-linear, only the stress strain relation is linear in this particular case. So you can think of a hierarchy of models here, right? So one is that materially linear, right? Materially materially non-linear and geometrically non-linear and geometrically non-linear. So this would typically be used for rubber type materials, okay? So rubber type materials. So this is just one example where you would use a materially non-linear because the Savannah Kickoff will not be able to capture the behavior of rubber type materials where you can have very large strains, okay? And so in that particular case you have to go for a materially non-linear and geometrically non-linear material model. Just one example of the model would be Ogden, Mooney-Rivlin and so on. Okay? Mooney-Rivlin and so on. Okay? Then the next hierarchy is that it is materially linear, but geometrically non-linear. And that is the Savannah Kickoff. So this is the Savannah Kickoff model. And then the last one is that materially linear and geometrically linear also, right? Geometrically linear. So this is linearized elasticity. Linearized elasticity, right? Which you have probably studied in some formal course, like ME242 and things like that, right? So this is the the crudest approximation, so to speak, right? So in this last one, materially linear and geometrically linear, you are allowing only very small perturbations about the reference configuration, right? So that we have seen that displacement should be small and the displacement gradient should also be small. Only then can you use the linearized elasticity model. Okay. Then what about the Savannah Kickoff model? Okay, so let us look at when the Savannah Kickoff material model can be used. Okay. So let us look at some examples. Okay. So suppose imagine that there is a cantilever beam like this, and then now imagine that you apply some load, okay, and it undergoes a very large displacement. Okay, so if you now look at this kind of a block, right, just a part of this cantilever, then you will see that actually the displacements are very large, but the strains are very small. Okay, in these kind of region here. So basically the displacements are large. Right? Displacements are large, but strains are small. But strains are small. So I mean, this kind of a situation can happen, right? So for example, if you just take a rigid motion, in a rigid motion you have like chi is equal to q of t times x plus c of t, right? So here you can imagine that this c of t can have any magnitude, right? It can just translate by any large amount, or even the rotation can be very large, and so but the strain would be zero, right? Even if the displacement is very large in this particular case, or the rotation is also very large, but the strain can be zero. Okay, so here, so this is an example. So this is very similar. So here, basically, the cantilever is undergoing a very large displacement, but it is of the nature of a rigid, almost rigid. Means it is not perfectly rigid, but almost rigid. So the strains, especially in this particular part here, will be small. But as I said, but the displacements are very large, let us say. So in that particular case, the use of the Savannah Kickoff material model would be appropriate. See, you cannot use linearized elasticity, suppose, if the displacements are large, because as I said, that linearized elasticity is appropriate only when the displacements are small. Both the displacement and the displacement gradients are small. Okay, but whereas in this particular case, the displacements are large, right? And so in this particular case, you cannot use linearized elasticity, and you have to use this large displacement, small strain model. So this Savannah Kickoff material model is also known as a large displacement, small strain model. Small strain model. Okay, so for that reason, it is known as this one here. Then even the Savannah Kickoff material model is not appropriate when the deformations, that means the strains themselves are large. So for example, that is what happens in a rubber type of material, right? So suppose if you take a rubber band and stretch it, right, you can get elongations of the order of 200%, 300%, right, easily. So in those cases, the use of the Savannah Kickoff material is also inappropriate, right? So then you have to go to the first category, that is the materially nonlinear and geometrically nonlinear material models. And examples of those material models which are appropriate for rubber type of materials are Ogden model, Mooney-Rivlin type of model, and so on. So there are lots of models for this one. So those would be the appropriate models to use when you have very large strains and large displacements. Okay, so this is the hierarchy of models. So you have to use the appropriate model for whatever case it is that you are studying. Okay, so you have to be very careful about the choice of material models. For example, as I already discussed, you cannot use the Savannah Kickoff material model when you have very large strains. Okay, so this is, as I said, that only, so basically this is very important. You can use it only when the strains are small and the displacements are large. Okay, and if the displacements are small and the strains are small, then you can use just the linearized elasticity model. Okay, so this is sort of a summary of the hierarchy of material models that one should use in a given situation. So you have to make a choice, right? Which particular thing which particular approximation out of these you would like to use in a given problem. Okay, now this let us look at whether the Savannah Kickoff material model satisfies frame indifference and isotropic. Okay, so this is the particular model. Now let us study this Savannah Kickoff material model a little bit in detail. So if I rewrite this, okay, so I can write this. So in place of E, you can write it in terms of C also. So right, you know the relation E is equal to half of C minus I. So use that, and then what you will get is that S at of C now is equal to lambda by 2 times I1 of C minus 3 minus mu times identity plus mu times C. And then now you can see that this is of the form gamma naught of invariance of C times identity plus gamma 1 of invariance of C times C. Of course, this gamma 1 of phi of C is just a constant, but still you can take that to be a function of the invariance of C, right? So because it is a special case of the more general form, right? So the last time we discussed this, that a material model is frame indifferent and isotropic if and only if it is of the form gamma naught of invariance of C times identity plus gamma 1 of invariance of C times C plus gamma 2 of invariance of C times C square. So let us call this a star. So this is just a special case of star. This is just a special case of star. And so here these are necessary and sufficient conditions, right? So the necessary and sufficient condition that a material be isotropic and frame indifferent is that S be of this particular form. So if S, since this is a special case of this, automatically we see that the Savannah Kickoff material model is both isotropic and frame indifferent, right? So the Savannah Kickoff is isotropic and frame. Because it is a special case of star, so hence this is a right. And okay, but as I said that you have to use this material model very, very carefully. So the use of this particular model is appropriate only when the strains are small. I already indicated that. So if especially under compression, actually this material model has very severe problems. Okay, so this is not an appropriate material model to use when you have very large compressions. Okay, that is one thing. And also The experience with eversion problem. So eversion means that suppose if you take a ball, like a rubber ball, and you cut it, okay, and then you can turn it inside out, right? So that is known as eversion. So the experience with eversion problems is that you can have very large strains but small stresses. Okay. So in the Savannah Kickoff material model, you can see that because it is linearly dependent on the strains, the stress is large if and only if the strains are large, right? So because from this you can see that strains are large if and only if the stresses are large. The stresses are large. But in eversion problems, so where you are turning it inside out, in eversion problems, the strain can be large, but stress is small. Stress is small. So in this case, Savannah is not appropriate. Savannah is not appropriate. Okay, so typically these eversion problems have to do with rubber type material. So I give the example of a rubber ball that you are cutting, right, and then you are turning it inside out, right. So that is just that is what is called if you take the rubber tubing on the handle of your cricket bat, correct, and that tube if you take and then if you turn it inside out, right. So we'll be studying those examples at a later stage when we discuss non-linearity and non-uniqueness of solutions in elasticity. So at that time we will be discussing these things, but at this particular stage I'm just giving examples of cases where the Savannah Kickoff material model is not an appropriate model to use. And so, I mean, before using the Savannah Kickoff material model, you should be very careful to see that it is being applied in the right scenario. I mean, you don't want to apply it in some place where its use is inappropriate. Okay, so that is something you have to be very careful about here. Yes, and I also indicated that under compression, you can get two different stresses for a given strain, and so lots of problems actually with this model. So as I said, that finally its use is appropriate only when your displacements are large and strains are small. Okay, so that is something, and but still it is a very good model because it is the first level non-linear model. Non-linear model in the sense that you are still having a geometrically non-linear problem, right? A geometrically non-linear relation. And so typically if you are writing a finite element code, you would first write it for a Savannah Kickoff material because that is the simplest non-linear model that you can think of. I mean, so if you just go one step above linear elasticity, then you are just simply making the strain displacement relation non-linear, but you are keeping the stress strain relation linear. So in that sense, it is just the very first increment into the non-linear domain, and so this is the simplest possible non-linear model that you can get, right? And so that is the reason that typically when we write non-linear codes, Savannah Kickoff is the first model that we will program in finite element code and so on, because it's easy to debug, right? You can easily get some analytical solutions and things like that. Okay, so now let us look at what are the bounds on this lambda and mu. Okay, so this lambda is this constant and this mu. So these are known as Lame constants here. So let us look at some bounds on these Lame constants now. where lambda mu are assumed to be constant. So that means not even dependent on x also, not dependent on x. Okay, so just that means you are assuming that the material is homogeneous also, right? So they are not dependent on x also. So these bounds that we are going to deduce are based on thought experiments. Okay, so let us look at that. Now, for the if you transform the second Kickoff stress expression that I gave for the Savannah Kickoff material to the Cauchy stress expression, then this is what we'll get. So tau is equal to 1 by j times lambda, so lambda times trace of E times B plus 2 mu times F times E times F transpose. Right? So this is what we will get. Plus some order E terms, plus order E. And so this we are not going to worry about again. So because we are assuming that E is small. Okay, so the first thought experiment that we will consider is simple shear. Simple shear. So we have already seen the kinematical mapping, the time mapping for this simple shear. So if you recall, it was just a block, and then it is the top surface of that block is moving by some angle gamma. So this is what we have already seen. So if you now substitute for B, F, E, F transpose for this particular situation. So I have already given you all the relevant quantities, kinematical quantities for this simple shear. So you go back to chapter 2, right, where we studied kinematics. So there we have already studied what the B is, F is, E is, and so on for this particular case. So if you substitute it into this, then what you will get is that you will get tau 12 is equal to mu times gamma plus order of gamma. So that is what we will get. Now you can see that if I apply a stress in this particular direction, I would expect this gamma to be positive. Right? So basically intuitively we expect that this gamma and this tau 12 have the same sign. I mean, so we generally it doesn't happen that you are applying a shear in this particular direction, but the block moves in the opposite direction, right? So intuitively we expect that your tau expect tau 12 greater than 0 if gamma is greater than 0. So gamma greater than 0 is in this particular direction here. So this implies that your mu is greater than 0. So consider that gamma is small enough so that this term dominates the other terms here, right? And then in that particular case, you would expect that the block moves in the direction of the shear traction that is being applied on the top surface here. And so mu is greater than 0. So that is the one bound that we get based on this one. Okay, then the second thought experiment is that of uniform compression of a sphere. So basically now you take a sphere, so this is your sphere, and apply uniform compression on all sides like this. Okay? So just apply a uniform pressure on the whole thing. So in that particular case, you would expect that the sphere compresses, correct? The volume decreases, right, if you apply pressure, right? So that is the intuitive idea that we have in that particular case. So uniform compression of a sphere. So this is second thought experiment. Uniform compression of a sphere. Okay. So in this particular case, your mapping chi is equal to 1 minus epsilon times x. Right? So this is the mapping, and then in this particular case, you will get that tau, the Cauchy stress is minus epsilon times 2 minus epsilon divided by 2 into 1 minus epsilon times 3 lambda plus 2 mu times id. So you can see that if you are this epsilon is the amount of compression that the sphere is undergoing, right? That is the reduction in the radius of the sphere, and so the stress is going to be a compressive stress, so that will have a negative sign. That means all these quantities are going to be positive quantities here, right? So since the stress should be compressive, since the stress should be compressive, when epsilon is greater than 0. So that is why this 3 lambda plus 2 mu should be greater than 0. Okay. So the first bound was that mu should be greater than 0. The second bound is that 3 lambda plus 2 mu should be greater than 0. Okay. So actually, what that implies is that the lambda can be negative also. Okay. So individually, if you look at the Lamé constants, then the lambda can be negative, but 3 lambda plus 2 mu should be greater than 0. Right. So that is the idea here. Fine. Now the third thought experiment. So that actually will help us link these Lamé constants to the Young modulus and the Poisson ratio. So that is something that we have seen in our strength of materials, right? So let us look at that. So now third thought experiment is uniform extension. Right? So this is a uniform extension. So by that I just mean this one here, right? We are taking a bar and then just applying a unidirectional traction here, and then so there will be a contraction in this particular direction, which is the Poisson contraction here, right? So in this particular case, what you will get is that, so this you take to be the one direction, suppose. So the traction is being applied along this one direction, and the 2 and the 3 are in the plane perpendicular to this one direction here. Then what you will get is that tau 2 is equal to tau 3 is equal to epsilon divided by 1 plus epsilon times lambda times 1 minus 2 nu times minus 2 times mu plus order epsilon. So the chi mapping that I am using is exactly the same as what I used for this particular case again when we did the kinematics chapter here, right? So because of that, so if you recall, we had this nu in that mapping, and so just the same mapping I am using to calculate this one. And now see, so because there is no stress that is being applied on the lateral surfaces, we expect that this stress should vanish here. So that means the first order terms vanish. Okay, so expect the first order terms to vanish. Expect the first order terms to vanish. So because of that, what you will get is that you will get mu is equal to lambda divided by 2 times lambda plus mu. Okay, so that just I am setting this whole thing to 0, and then this is what I will obtain from that. So okay, and then now let us look at what is the tau 1 right, from this. So you will get tau 1 is equal to epsilon by 1 plus epsilon 1 minus mu epsilon square times lambda times 1 minus 2 mu plus 2 mu plus order epsilon. And if you now substitute for mu, so this expression if you substitute into this, then what you will get that this is equal to epsilon into 1 plus epsilon divided by 1 minus mu epsilon square times mu times 3 lambda plus 2 mu divided by lambda plus mu, right? Plus order epsilon. Okay, and then we expect that this should be equal to E times epsilon, where E is your M modulus. So this is exactly like your unidirectional stress strain curve, right? So this is your tau and epsilon, and the slope of this is E. So this whole thing should be equal to E times epsilon plus order epsilon, right? And so if you now compare these particular terms, then what you will get is the following relation now. Now what you will get is that from this you will get that E is equal to mu times 3 lambda plus 2 mu divided by lambda plus mu. Okay. So these are the relations. So maybe I will just summarize all these relations here, whatever you get. So let's see. So you will get that, so this is the relation that you get. And the other relation we had was that mu is equal to lambda divided by 2 times lambda plus mu. Okay? And then you can invert these relations. So from this, what this will imply is that lambda is equal to E times mu divided by 1 plus mu times 1 minus 2 mu, and mu is equal to E divided by 2 into 1 plus mu. So, I'm sure you must have seen this derivation within the context of strength of materials. So, just that we have derived it in a slightly different way. This is nothing but the shear modulus, basically. So, in the beginning, we did not assume that the Lamé parameter mu was the shear modulus, but it has just turned out that it is a shear modulus. Right? This is also the shear modulus, because this E by 2 into 1 plus mu, so shear modulus. So basically, like typically we will denote it by the letter G. Right? So that is, so this turns out to be the same as that shear modulus. Yeah. And then now we can deduce bounds on E and mu from the bounds on lambda. Right? So let us do that. So we now have that mu greater than 0. Right? We have seen this mu greater than 0, and 3 lambda plus 2 mu is greater than 0. So this implies that E is greater than 0 and minus 1 less than mu less than half. Okay, so these are the bounds that you get. So lambda plus mu greater than 0 and 3 lambda plus mu greater than 0 implies that E greater than 0 and minus 1 less than mu less than half, and E greater than 0 and minus 1 less than mu less than half implies that mu greater than 0 and 3 lambda. So it's an if and only kind of statement here. So the interesting part, of course, is that the Poisson ratio can be negative. So that means what is the physical implication of that? Right? So the physical implication is that if you now pull in this particular direction, it expands rather than contracting. Right? So in the lateral direction, so suppose if you are pulling this, in the lateral direction also it is expanding. Okay, so the volume is effectively increasing, right, when the Poisson ratio is negative. But that is not a problem, right, because there is no such thing as a balance of volume, right. So it's basically just a balance of mass, not a balance of volume. So volume is allowed to increase. Correspondingly, the density will decrease, so that the product of the density times the volume will ensure that the mass is conserved, but the volume can increase, right, if you have a negative Poisson ratio. So at least theoretically, we can allow for a negative Poisson ratio. Now, the next question is that whether such negative Poisson ratio materials actually exist in nature. Okay, and so the answer is that there are certain foam type of materials where the Poisson ratio is negative. Okay, but now the next question is that these foam type materials, they have pores in them, and then whether now when you have material that has pores in it, whether that can be considered as a continuum. That is the question here. So so if you are willing to accept that as a continuum, then okay, you have a negative Poisson ratio. But if you feel that something which has pores in it is not a continuum material in the strict sense of the word, then actually, as far as I know, we do not know of any actual materials where the Poisson ratio is negative. Okay, so but that I'm sure there is a lot of literature on this about negative Poisson ratio materials. So if you do a web search, you may be able to locate some of these things, right? These foam type materials and things like that. Okay, the one important thing that I want to note at this particular stage is that, see, these bounds that we deduced, right, they were based on thought experiments, right? So we are just saying that, okay, we have this intuitive picture of what should happen when we are conducting the experiment of simple shear or of uniform compression of a sphere, and so these are based on thought experiment, but they are not deduced using the second law of thermodynamics. Okay, so at a later stage we will see that if you take a fluid, for example, right, the bounds on the viscosity coefficients will come out of the second law of thermodynamics, right? But in the case, unfortunately, in the case of elastic materials, or even in the case of a nonlinear elastic material, thermodynamics imposes no restrictions whatsoever. Okay, so the second law of thermodynamics, you will see, will impose no restrictions on these Lamé parameters. Okay, so they can be anything according to the second law of thermodynamics. So these bounds are actually based more on the thought experiment only. Okay, so that is one thing, one very important thing that I would like you to note here. Okay, so we will move to the next topic now, which is hyperelastic material. And so this is a very, very important topic that we are going to discuss now. So hyperelastic materials. Elastic material is said to be hyperelastic if there exists a stored energy function or strain energy density function. From V0 plus to R such that P hat of x comma f is equal to del W hat by del f evaluated at x. F for all x belonging to V0 and f belonging to limit plus, or in component form. Component form is Tij is del W hat by del Fij. So this is the component form of this particular relation here. So it's basically the gradient of the strain and density function. So basically it says that an elastic material is said to be hyperelastic if there exists such a stored energy function. So in the mathematical literature we will use this term, stored energy function. And the engineering literature will typically use strain energy density function. So let's call it W hat, such that the first pure of stress is the gradient of the strain energy density function with respect to f. Okay, so now actually we can see that the class of hyperelastic materials is a subset, right? So this is your elastic material, and these are your elastic materials. So this outer set is elastic material, but typically, so actually, because theoretically speaking, there can be elastic materials which are not hyperelastic, right? But typically in the literature, you will see that if they assume a material to be elastic, they also assume it to be hyperelastic. Okay, so typically, I mean, you will not find any material model which is elastic but not hyperelastic. So typically, as I said, that for all elastic materials, at least whatever literature that I have looked at, they will typically immediately assume it also to be hyperelastic. And actually, the reason for that is that there are very strong thermodynamical reasons for why you can assume an elastic material to be hyperelastic. So especially, so suppose if the process that the material is undergoing is an isothermal process or an isentropic process, then we can rigorously show that the free energy function acts like a strain energy density function. So at least in those two special cases, isothermal and isentropic, we can rigorously show that the strain energy density function always exists. Okay, for other cases we do not know, but as I said, that typically we will still assume that a material is always hyperelastic. Okay, and so this. Now the next question that arises is that why is it that we are defining the first Piola-Kirchhoff stress in this particular way? Why not the second Piola-Kirchhoff stress, or why not the Cauchy stress? Okay, so the reason is that if you take this particular definition, then you will see later that you will get relations like W hat of x comma qf is equal to W hat of x comma f. Okay, so this is something that we will show. So that this kind of a relation is the appropriate relation for a scalar value function, correct? Objective function or material frame indifferent function. And so that this kind of a relation follows only if you adopt this particular definition here. And so we want the strain energy density function to be objective in this particular sense, and that is why we define. So this here is the definition. Okay, so that the first Kirchhoff stress is a gradient of this strain energy density function here. Okay, so before proceeding to the next theorem, let me just point out some conservation laws, okay, that an elastic material will obey. So let us look at that. Okay, but just before that, let me just make one comment that just like there is a hyperelastic material, there is also a hypoelastic material. So let me just mention that briefly. So hypoelastic material. Okay, so there actually your the stress rate would be, so the stress rates like what we discussed, right, the Yauman stress rate and the Truesdell stress rate would be related to the rate of deformation tensor. Okay, so so let us take that tau, that diamond or whatever is a function of d. Okay, so these kind of models have also been used to model elastic materials, but there are actually lots of shortcomings of these hypoelastic material models. So for example, if you load an elastic material and then you unload it, right, then it should come back to the zero stress rate if the strain is zero. But if you use these hypoelastic material models, you may not come back to the same strain, to the zero state, right, on unloading. And so this has very, this has a lot of shortcomings in it, the hypoelastic material model. And so generally, the literature doesn't adopt this hypoelastic material. So almost the whole literature will assume it to be hyperelastic in that particular case. But you should know that some such thing. So there are a few groups who also use the hypoelastic because they claim that it's a good approximation. So it may not be perfect in the sense that, as I said, that on unloading it doesn't give zero stress, but they claim that it's a good approximation, and so there are some groups who still use these hypoelastic material models. Okay, so on the left hand side, you have typically you have a stress rate like the Yauman stress rate or the Truesdell stress rate and the Green-Nagli stress rate and so on, and on the right hand side, it's some function of the rate of deformation and things like that. Okay, but we will not go into the hypoelastic at all. We will focus only on the hyperelastic material models in this particular course here. Fine. So now let us look at certain conservation laws, right, which follow from this one. So, from the mechanical energy balance, okay, can be written as follows. So del W hat by del T is equal to del W by del F times m dot. Right? And so this is nothing but T times m dot. So if you recall, there was an expression like T times m dot in the mechanical energy balance. So you can replace that T times m dot by del W by del T because of this chain rule. And then you can write the mechanical energy balance as d by dt of rho naught chi dot chi dot by 2 plus W hat of x comma f of x comma t times dv naught, this is over v naught, is equal to integral of chi dot times t naught times ds naught. So this is nothing but the velocity. Chi naught is nothing but the velocity plus integral of rho naught chi dot v naught times dv naught over v naught, and this is over x naught, the surface of the reference configuration. So here, or you can also write in this in the deformed configuration also. So I will not go into that, but basically you can see that if your chi dot t naught is equal to 0 and your chi dot v naught is equal to 0, then you will see that the energy is conserved, right? So then you will get that half of rho naught times del u by del t times del u by del t, keeping x fixed, plus w hat, the whole integral of this. So this is over v naught is times dv naught is equal to a constant, right? Because the right hand side has become 0, correct? And then d by dt, so you integrate this with respect to time, and so this whole thing is a constant. And obviously this constant is going to be the value of this particular integral at time t equal to 0. Right? So that's so this basically quantity says that the kinetic energy plus the strain energy remains a constant, right? If this chi naught dot t naught is equal to 0 and chi naught dot d naught is equal to 0, or in particular if your load itself is 0 and your the body force itself is 0, then in that case the sum of the kinetic energy and the strain energy is conserved, right? So I mean, you can imagine that let me just give an example. So suppose if you have a cantilever beam, right, and then you now suddenly apply some load f of t, which is varying with time. Okay, so now it deflects, okay, some load, and now you leave the load. Okay, so that is you remove the load. Then now it will keep oscillating, right, like this, and now you will see that these conditions are satisfied, correct, because the chi naught dot is equal to 0. The tractions are not 0, but the chi naught dot is equal to 0 on this particular part, and on the remaining part there is no traction. So this condition is satisfied. So this beam will now continue to oscillate like this, right? So now in the next thing it will go like this. So it will just continue to oscillate, but the total of the kinetic energy and the strain energy will be conserved in that particular case. So at this extreme position, right, the lower extreme position, the kinetic energy is going to go to 0, right? Because the velocity goes to 0 at that particular, at that extreme point. But the strain energy is a maximum, right? And then if it comes to the middle position, then now the kinetic energy is a maximum and the strain energy is 0, and then again it gets converted to strain energy as it reflects upward. So the sum of this quantity remains constant. So this is just one example. So similarly, the linear momentum and the angular momentum are also conserved, not in this case because the traction is not 0 here, but in cases where the loads are 0. Right? So let us look at that also. So if the B naught and T naught are 0, in that case the linear and angular momentum are also conserved. So if B naught equal to T naught equal to 0, correct, and then then it follows that integral of rho naught times del U by del T. So this is your linear momentum times dV naught equal to a constant, right? So the linear momentum is constant. Linear momentum constant. So that gets conserved, and then similarly your angular momentum will also be conserved. So chi or x cross del U by del T, keeping capital X fixed, dV naught is equal to a constant. So this is over V naught, this is also over V naught. Okay, so this is the angular momentum conservation, right? Angular momentum conservation. And as I already discussed, the energy would also be conserved if your T naught and V naught are equal to 0. Right? So that's the idea here. Fine. So now these are some of the conservation principles that hold. You have already seen applications of this in your undergraduate days, but now we are just expressing this whole thing in a more rigorous fashion, right? In terms of the strain energy and so on. So this is something you may not have seen in your undergraduate days. So this is we are saying that the sum of the kinetic energy and the strain energy is a constant, right? That is something. Okay, so now let us move on to the next thing here. That is now let us look at the strain energy density function for an isotropic material. Okay, so let us first derive the particular theorem. So ultimately we want to look at the strain energy density function for an isotropic material, but first let us just impose the condition or constraint of framing difference, okay, and then see what the implications of that are. So theorem. So the stored energy function, the stored energy function W hat from V naught cross then plus to R is framing different. And if and only if at all x belonging to V naught, your W hat of x comma qf is equal to W hat of x comma f for all f belonging to min plus and q belonging to all plus here, and or equivalently if and only if there exists a function W tilde from V naught cross P sim to R such that W hat of f, W hat of x comma f is equal to W tilde of x comma f transpose. So basically the dependence on f goes to a dependence on C if we assume that the material satisfies material framing difference. So as I said, material framing difference is an axiom, right? And so we are always going to assume that material framing difference holds, right? And so basically what the conclusion is that for a framing different material, the dependence on f will go to a dependence on C, that is the right Cauchy-Green straight tensor. Okay. So let us now prove this particular theorem. Okay, so the condition for the framing difference for a first pure across stress is the following, right? So for so T hat of f is framing different. Effectively, T hat of Qf is equal to Q times T hat of f. Okay, so this condition we obtain from the condition that tau hat of Qf is equal to Q times tau hat of f times Q transpose, right? So this is the original condition on the Cauchy stress. Then from this we can derive the condition on the first square across stress. Okay, so the T hat of f is framing different if and only if it satisfies this particular condition here. Right. So this I can also write as T hat of f is equal to Q transpose times T hat of Q times f. Okay. So I'm just rewriting it in this particular way by using the properties of a proper orthogonal tensor, and T hat of f is nothing but so del W hat by del f evaluated at f is equal to Q transpose times del W hat by del f evaluated at Qf. Okay. So now basically we need to compute these gradients. Okay, so this, especially this gradient of this particular function here. So let us define now a new function. So let me just write it here. Yes, so let us write this so that WQ of f be defined as W hat of Q times f. Okay, so just I mean we are just renaming this particular function as W hat of Q of f. So the Q, because the Q is going to remain fixed. So that is why we are simply putting that as a subscript in this particular case. So this is for a fixed Q. For a fixed Q belonging to all classes. So now I need to find the gradient of this particular function, right? So that this gradient del W by del f of Q of f. So basically this now is that WQ of f, and I need to find the gradient of that particular function here. So W hat of Q of f plus U, right? We have to perturb that. Q is fixed. So this is equal to W hat of Qf plus Qu, which is equal to W hat of Q times f plus del W hat by del f of Qf matrix inner product Qu plus order of Qu. Right. Okay. And then this we can write as equal to W hat of Q. Okay. Use this definition here. So that is W hat of Q of F plus Q transpose times del W hat by del F and QF times U plus quantity. So here I am using the fact that A matrix in our product B, C is D transpose A matrix in our product C. So I am just using this particular property to write it in terms of this Q transpose just comes from this side, and then I can write it in this particular way here. Okay, so that means, so now this implies that, so the first order term is the gradient. So that is what we have seen here, right? So that is del W hat of Q evaluated at F, and the gradient is with respect to F, that is equal to this Q transpose times del W hat by del F evaluated at QF. Okay. So now let us now compare these two things here. Okay, so let me just rewrite this. Yes, so you can see now that this term is the same as this particular term here, right? The Q transpose times del W by del F, and so the left hand sides also have to be the same. Okay, so let us call this as 1, let us call this as 1, let us call this as 2, right? So from 1 and 2 what we get, so from 1 and 2 what we get is that del W hat by del F minus del W hat Q of F by del F is equal to 0. They have to be the same. And so now we can simplify this. So let us write this. So this implies now that del by del F of W hat minus W hat of Q of F is equal to 0. So that I am just taking the derivative sign outside of this one here. And this is valid for all F and for all Q. This is valid. So this is valid for all F belonging to lin plus and Q belonging to all plus. Okay. Now, see, again, if you go back to the statement of a theorem, it's an if and only if statement that we have. That means if W hat equal to WQ of F, then it is framing different, and conversely, if it is framing different, then you add W hat equal to W hat of Q. So let us now try to show this. So, okay, so now if W hat of F is equal to W hat of Q of F, then let us call this as star. So then star is satisfied. Okay? Then star is satisfied, and so then the material framing difference is also satisfied. Conversely, now we also need to show the converse. So conversely, if star holds, we need to show that this particular statement is true. Correct? So if conversely if that is true, then star then we have that W hat of Q of F is equal to W hat of F plus C of Q. Right? So that is what we get. Now we want to show that the C of Q is equal to 0. Correct? Only then we will get this particular relation. So that so first you take F equal to I. So take F as equal to I. Okay? Then what you will get is that W hat of Q is equal to W hat of I plus C of Q. That is what you get. And now you take f equal to q. Now next you take f is equal to q itself. Okay. Then what you will get is that w hat of q square is equal to w hat of q plus c of q. Okay. And then you substitute. So w hat of q is already available in this particular expression. You substitute that into this particular expression. Then what you will get is that this is w hat of I plus 2 times c of q. Okay. And so you continue this whole process, and then what you get, so if you continue, so dot w hat of q to the p is equal to w hat of I plus p times c of q. Okay. Now you can see that we always assume that the strain energy density function remains bounded, correct? So this is an admissible deformation because determinant of f is, so suppose if f is q to the p, suppose if f is equal to q to the p, then determinant of f is equal to 1, correct? So this is an admissible deformation, and then if it's an admissible deformation, then the strain energy remains bounded. So this term is bounded, this term is bounded, but this term becomes unbounded as p tends to infinity. Correct? So as p tends to infinity, p times c of q is unbounded. Correct? It's unbounded unless c of q is 0. Correct? So basically we are saying that so the c of q has to be equal to 0, because otherwise you have bounded, unbounded, right? If c of q is not equal to 0, so that shows that c of q has to be equal to 0, right? And so fine. So let us now write this. Yes. Okay. So what we have now shown is that w hat of qf is equal to w hat of f, right? So that is what we have now shown for material frame difference to hold, right? And so this is an independent state. Now there is a second part to that particular theorem, that we say that the dependence on f reduces to a dependence on c, that is the right Cauchy-Green strain tensor. So let us try to show that. So let's take so f is equal to r times u, right? So where r belongs to r plus, right? And so that is exactly of this particular form, right? So this is of the form of ru, and so what we can do is that let us just write this. So this is w hat of f is equal to w hat of ru, correct? And this has to be equal to w hat of u. So because in this particular case your u belongs to ln plus, u belongs to ln plus. In fact, it is positive definite. So definitely that the set of positive definite tensors is a subset of ln plus, right? And so we can apply this particular theorem. So this is for all f, this is for all f belonging to ln plus, correct? And so u definitely belongs to this particular set, and so I am just applying it to that u. So this is equal to w tilde of f transpose, right? So this is what we get here. And that is because your u is the square root of this one, right? So that is because u is equal to square root of c, and so this the way I am defining this w tilde of c is equal to w hat of square root of c, because u is a square root of c. So I am just defining this function in this particular way here, right? Okay, and then the converse of this also we need to show. So what we have shown is that if it is if the material is framed different, then there exists a function w tilde such that w hat of f is equal to w tilde of the right positive restraint. Conversely, if there exists such a function, that is w hat of f is equal to w tilde of f transpose f, then the material is framed different. Okay, so let us do this converse. So if conversely w hat of f is equal to w tilde of f transpose f, then now we need to show that w hat of q of f is equal to w hat of f. So that let's just show that. So q of f is equal to now w tilde. So now qf plays the role of f. So wherever f occurs, you will put q of f. So you will get that this is f transpose q times f, and this is nothing but w tilde of f transpose f, which is equal to w hat of f. So we have shown that w hat of q of f is equal to w hat of f, and hence material framing difference is satisfied here. Fine. So we will continue this discussion next time.